Titanoboa wasn't what you think you've seen it. The massive snake coiled around a crocodile, dragging it underwater, crushing it to death. The ultimate prehistoric predator. A reptile so powerful it hunted other giants. That image is in documentaries, museum displays, on every YouTube thumbnail for the last 15 years. It's wrong, not slightly wrong, not missing a few details. The most famous thing everyone knows about the largest snake that ever lived is a story that was never in the science. It came from a press release. It spread through journalism, it was repeated by documentaries, and now it's treated as fact by nearly everyone who's ever heard the name Titanoboa. But the real story, the one the bones actually tell, is stranger than the myth, and it starts not in a laboratory, not in a museum, but in a coal mine, Cerrejón, northern Colombia, one of the largest open-pit coal mines on Earth. In 1994, a geologist working the site found a chunk of rock he couldn't identify. He turned it over, examined it, decided it was a piece of petrified wood. He labelled it accordingly, Petrified branch, and placed it in a glass display case in the mine office. It sat there for nearly 10 years. In 2003, an undergraduate student on a field trip to the mine noticed something in the sandstone, not the fossil in the display case. Something in the rock face, ancient tropical leaves, preserved with extraordinary precision. Species that didn't match anything in the fossil record for that region. He brought samples to a botanist at the Smithsonian Institution. That's what got the scientists to Cerrejón. They came for the plants. While they were there, one of them looked through the locked glass of that display case and photographed the forgotten fossil inside. The image was emailed to a vertebrate paleontologist at the University of Florida. The response came back within hours. That wasn't petrified wood, it was a jawbone. The first bone of a Paleocene land animal ever found in tropical South America. They went back, they broke the glass, they pulled the fossil out and found a second bone hidden directly behind it. That discovery triggered the 2004 expedition. A full team descended on the mine's La Punta pit. What they pulled from the ground was extraordinary. Ribs the length of your arm, vertebrae the size of your fist, pelvis fragments, turtle shells over 5 feet across. The scale of the bones was unlike anything the team had encountered. And then they made a mistake that would hold for 3 years. Because nothing that large had ever been a snake, every oversized bone was assigned to the default category, crocodile. Giant bones plus tropical prehistoric environment equaled crocodile. The logic was automatic. The crocodile pile grew enormous. The unknown pile stayed nearly empty. In 2007, a graduate student in a Florida lab was sorting through a shipment of those crocodile bones when he picked up a vertebra that didn't match. The shape was wrong. The proportions were off. A colleague walked over, pulled a vertebra from a modern anaconda in the university's reference collection, and held the two side by side. Same architecture. Completely different scale. That's a snake. The formal scientific description was published in Nature in February 2009. They named it Titanoboa cerrejonensis, the Titan boa from Cerrejón, 13 meters long, 1,100 kilograms. The largest snake ever scientifically documented. Those numbers require a moment. The green anaconda is the heaviest snake alive today. A record specimen, the absolute ceiling for a modern snake, might reach 6 meters and weigh close to 100 kilograms. That is the biggest snake the current world produces. The smallest Titanoboa individuals recovered from Cerrejón were already larger than that. The largest Titanoboa was roughly twice as long as the biggest anaconda ever measured, more than 10 times as heavy. At its widest point, the body would have been approximately 1 meter thick. If you stood beside it, the body would reach your waist. If it slithered down a hallway and decided to pass through a doorway, it would have to squeeze to fit. One of the researchers described it this way. It was as long as a school bus, as heavy as a small car, built like nothing the world currently contains. But these numbers came with a problem. They were calculated from vertebrae and ribs, the snake's body, not its head. Snake skulls are composed of dozens of loosely connected bones, and those bones almost never survive fossilization intact. They disarticulate, they scatter, they disappear. So for the first few years after the discovery, scientists knew precisely how massive Titanoboa's body was and had almost no information about what its head looked like. No skull meant no information about bite mechanics, jaw structure, or what the animal actually ate. That absence was important, because without a skull, the diet question stayed open. And into that open question, a story moved in. The story was simple. The environment that preserved Titanoboa also preserved crocodilian fossils. Large predatory reptile plus large prey reptile in the same formation equaled one eating the other. The press coverage of the 2009 paper ran with it. Documentaries repeated the coverage. The image of the giant snake coiled around a crocodile became the definitive portrait of Titanoboa before anyone had found the skull that would determine whether it was even anatomically plausible. Then, in 2011, a Smithsonian intern working at La Punta pit found something that changed everything. 3 disarticulated Titanoboa skulls, in a species where finding one would have been remarkable. The skulls were approximately 40 centimeters long. When scaled against the rest of the skeleton, they pushed the total length estimate upward to 14.3 meters. But the revised length wasn't the significant finding. The skull architecture was. Here is what the skull actually showed. Snake skulls are diagnostic. The way the bones connect, the size and anchoring of the teeth, the geometry of the jaw articulation, all of it reflects what the animal ate and how it caught prey. A constrictor built to take large struggling prey has a specific design: wide gape, strong jaw articulation, robust, deeply anchored teeth designed to grip and hold something that is fighting back. Titanoboa's skull matched a completely different design. The teeth were numerous but small, weakly anchored, not deeply set, recurved slightly backward toward the throat. The articulation points between the skull bones were reduced, mobile and flexible, rather than mechanically powerful. The overall architecture matched the skull pattern seen in modern file snakes and sea snakes, dedicated fish hunters. Animals that snatch slippery prey from water and guide it toward the throat rather than clamping down on something that struggles. The conclusion drawn by the researchers was unambiguous. Titanoboa was primarily a fish eater. The most likely prey, the giant lungfish of the Cerrejon Formation, some of them over 3 meters long, living in the same rivers. This did not mean Titanoboa never touched a crocodile. Modern anacondas take caimans regularly, and a 12-meter constrictor could kill a 2-meter crocodile without difficulty. Occasional predation is plausible, but occasional predation is not the same thing as being built from the skull downward to hunt crocodiles. Titanoboa was not built that way. The skull said something else entirely, and here is the detail that makes all of this stranger. No direct stomach contents from Titanoboa have ever been found. No bite marks on other animals that match its teeth. Every dietary conclusion, including the fish hunting conclusion, is inference drawn from skull anatomy and comparison to living species. The science is solid, the reasoning is careful, but nobody has ever documented Titanoboa in the act of doing anything. We are reading the engineering and inferring the intention. Which brings us to the argument Titanoboa started, the one that's still running. Cold-blooded animals can only grow as large as their environment allows. The metabolic ceiling for a reptile is set by ambient temperature. Warmer environment, higher ceiling, larger possible animal. The logic runs in both directions. If you know how large the animal got, you can work backward and estimate how warm the environment must have been. The team behind the 2009 paper did exactly that. They took Titanoboa's body measurements and plugged them into a mathematical model linking snake size to ambient temperature. The result: a mean annual temperature of 30 to 34 degrees Celsius for equatorial South America during the Paleocene, 4 to 8 degrees warmer than the same region today. That number landed in climate science like a stone through glass. The leading hypothesis at the time was called the tropical thermostat. The core idea was that even during extreme greenhouse warming events, the tropics self-regulate. Temperatures spike at the poles. The equator stays relatively stable. It was a foundational assumption in how scientists modeled past climate states. Titanoboa's body was direct physical evidence against it. If the tropics were cool during the Paleocene, this snake could not have existed at this size. Its body was not a model or a simulation. It was a measurement. A meter-thick vertebra-by-vertebra thermometer preserved in Colombian coal. The response from the climate science community was fast and came from multiple directions simultaneously. The first challenge pointed out that the same mathematical model, applied to a large Australian lizard from a later geological period, predicted the lizard should have reached 10 to 14 meters. It didn't come close. The model was overshooting. The largest animal in a given region doesn't necessarily represent the maximum possible size for that environment. It represents the largest one that happened to evolve. The ceiling and the occupant are not the same thing. The most structurally damaging challenge came from biophysics. A team argued that a snake weighing over 1,000 kilograms would face the opposite thermal problem, not being too cold to grow, but being too hot to survive. At that mass, the ratio of surface area to body volume is so unfavorable that the animal generates more metabolic heat than it can shed. In warm ambient conditions, it would overheat. This was not a trivial objection. If correct, it meant the ambient temperature during the Paleocene had to be lower than the model predicted, not higher. The snake's own biology was arguing against the temperature estimate. The Titanoboa team pushed back. They argued the snake was aquatic, like a modern anaconda, and water dissipates metabolic heat far more efficiently than air. The overheating critique assumed a land animal. An aquatic animal of this size would have solved the thermal problem by staying in the river. They conceded the upper end of their temperature range was probably too high, but held the core conclusion. The tropics during the Paleocene were meaningfully warmer than today, and the thermostat hypothesis was wrong. The debate has not been fully resolved. Papers continue to be published on both sides. Titanoboa's body is now woven into climate arguments that have nothing to do with snakes and everything to do with how the planet manages heat. What happened to Titanoboa after the Cerrejon formation is genuinely unknown. The fossils are found in one place. They represent one period. Before a major warming event called the Paleocene-Eocene thermal maximum, roughly 56 million years ago, Titanoboa is present in the record. After that event, it isn't. Whether the gap represents actual extinction or simply the absence of suitable rock formations from that time period in that region is impossible to say. The tropical fossil record for that part of the world during that window is nearly non-existent. The formations that would contain the next chapter either eroded away, were never deposited, or haven't been excavated. It's possible Titanoboa persisted for millions of years after Cerrejon. It's also possible the warming event killed it off. We have no way to distinguish between the two. What we do know is that no snake ever came close to filling the niche again. The world that produced Titanoboa was brief and specific. 60 million years ago, the Cretaceous extinction was 5 to 7 million years behind. The age of large mammals had not yet begun. Every apex predator role on land was empty. Into that vacuum, in a tropics that were genuinely hotter than they are today, in a river system full of giants, turtles 2 meters across, crocodilians approaching 5 meters, lungfish 3 meters long, a snake grew to a size the world hasn't seen before or since. After the Eocene warm period peaked, Earth entered a cooling trend that lasted 40 million years. The metabolic window that allowed cold-blooded animals to occupy apex roles narrowed steadily. Mammals grew larger, faster, warmer. The crocodilians held on longest in South America, reaching massive sizes well into the Miocene. But eventually the ceiling came down, the window closed. The green anaconda, the closest living relative of Titanoboa's lineage, weighs 1/10 as much. That gap has been open for 56 million years. Nothing has crossed it. In 2024, researchers described a fossil snake from India, Vasuki indicus, estimated at 10 to 15 meters. If the upper estimates are confirmed, it could challenge Titanoboa's record. The analysis is ongoing. For now, Titanoboa keeps the crown. Here is what stays with you about this animal. The first fossil was labelled petrified wood and left in a display case for 10 years. The skeleton was sorted into the crocodile pile. The diet was invented by journalists and repeated by documentaries until it became indistinguishable from fact. The colour, every rendering you have ever seen, the dark greens, the muddy browns, the iridescent scales, is completely fabricated. No skin has ever been recovered, no scales, no pigment. Every image of what Titanoboa looked like is a guess made by comparing it to anacondas alive today. Almost everything the public knows about this animal is either wrong or unsupported. But the actual science is more interesting than the myth. A world 5 million years past the worst mass extinction in 66 million years, the apex predator roles still empty, the tropics running warmer than anything alive today can survive in, and in the rivers of what is now a Colombian coal mine, an animal too large for the doorways we build, too strange for the categories we assumed, and too informative to reduce to a monster coiling around a crocodile. Titanoboa wasn't what you think. What it actually was is harder to picture, and it is, bone for bone, more extraordinary.